Dear students, in this video we are going to solve one problem from suspension cable bridge with a stiffening girder. The problem statement is a suspension bridge of 200 meters span has two numbers of 3-inch stiffening girder supported by two cables on both sides having a central dip of 25 meters. The width of roadway is 8 meters. The roadway carries a dead load of 0.5 kilonewton per meter square. It is given in meter square. We have to note the point that normally the load will be given in kilonewton per meter. Here it is represented as the area load, which is extending over the whole span. The dead load is extending over the whole span and a live load of 1 kilonewton per meter square. This load is also an area load which is over the left half of the bridge. It is only acting over left half portion of the bridge. Find the bending moment shear force at 60 meter and 150 meter from the left hinge. Also calculate the maximum tension in the cable. So normally we have to understand the procedure of the cable analysis with stiffened girder. So the cable is on the top, whereas the stiffened girder, which is the beam member, it can be in the form of truss, which is located at the bottom, where the traffic will be allowed. So normally the live load will be locating at the girder position only. So the girder position supported here and the cable is also supported at the top points. So the dip, that is the depth of cable is 25 meter, which is given, and the cables are suspended from the cable to girder like this. So this is one side view. If we draw some three-dimensional view for the other side along the road width, so we will have another cable on the other side. Okay, so it will be like this, and at the bottom we will have the truss like girder for the load transferring, and the suspenders will be tied between the cable and the girder. So normally the load transferring mechanism is from the girder to cable and cable to the supporting tower and the anchorages. So here we are given with two numbers of 3-inch stiffening girder. That is one number on the one side, another number on the other side. So the load is given as the area load. So if it is half left half portion means the load is given as the area loading, which is acting over the particular area. That's why it is in kilonewton per meter square. So the half of the road width is fully covered with a particular live load of 1 kilonewton per meter square, and the dead load is normally the load by self weight of the cable. The dead load is normally the self weight of the cable, which is also specified as a area load. So we have to convert into an UDL for our calculation. So you have to keep in mind that two numbers of 3-hinged stiffening girder is given. So we have to divide the load by 2 to get or to analyze only one stiffening girder. Normally our analysis is only 2D. So one side of the two stiffening girder is going to analyze. So here this is the view, and also it is 3-hinged stiffening girder. There are two support reactions in this. One is at the girder level, another one is at the cable level. So we will have both the vertical reactions and the horizontal reactions at both locations. I am naming as VA dash is the horizontal vertical reaction at girder level and VB dash at support B, and H is the horizontal thrust at the girder level. I am indicating it is H1 at the girder level, and the suspenders are specified like this. So if the problem is given as an area load, you have to convert into equivalent UDL for our calculation. Otherwise, the problem is very normal. That is to find out the moment, bending moment, and shear force, and the maximum tension. So maximum tension is calculated at this point. So the cable tension is always in this direction. So we need to calculate T max. So for the T max calculation, we require the support reaction VB and the horizontal thrust H, the horizontal thrust H. So why I am mentioning as H means this H will be the combined effect of the horizontal thrust due to this girder and the combined effect of the horizontal thrust due to this cable. So our analysis should be done as follows. That is, first one is girder analysis. Second one is the girder load can be converted into equivalent UDL or we can proceed. So first one is girder analysis, second one is cable analysis. Because the load from girder is transferred to the cable, so you have to analyze the beam first. So for that, the given parameters are length equal to 200 meter and width equal to 8 meter and dip D equal to 25 meter and dead load equal to 0.5 kilonewton per meter square and live load equal to 1 kilonewton per meter square, and our location for finding the shear force and bending moment is 60 to overall 200, so center point is 100 meter, so 60 meter from the left hinge, and if it is 150 it crosses the midpoint 150 meter, or it can consider 50 meter from the right side because it is a three-hinged stiffening girder which is in parabolic in the profile. So we need the x distance for the calculation of y, the ordinate y from the linear point from any one of the edges. So it crosses the midpoint 150 meters. So consider 50 meter right, which is equivalent to 150 meter from the left. So the first section is 16 meter. The second position you can consider as 50 meter from the right side. First step, girder analysis. So we consider the girder is a simply supported girder. It is subjected to an UDL, half of the span, because it is mentioned in the problem. So 100 meter span, which is it is acting, but the load is in kilonewton per meter square. So in stiffening girder bridge, the girder is acted upon by the live load. The girder is acted upon by the live load only. Because in girder we have bending moment and shear force, where in the cable the bending moment is not present and shear force is not present because both are zero. In girder, you can calculate the bending moment and shear force. It is subjected to only the live load. The dead load means the cable, the self weight of the cable is the dead load. So it is not accounted in the girder analysis. The dead load is not accounted in the girder analysis. Only the live load is accounted for our calculation. So the live load is 1 kilonewton per meter square, and also we have to note both the sides of stiffening girder is considered for this load because it is an area load. So we have to divide it by 2 for getting one side load. So first of all, half of the load of one is kilonewton per meter square. We need the load per meter length of the run, per meter length of the run. So multiplied with the width of the road, multiplied with the width of the road. So half into 1 into width is 8. So the UDL is 4 kilonewton per meter. The UDL is 4 kilonewton per meter. Okay, 4 kilonewton per meter. We can specify the support reactions VA dash and VB dash and half of the loading. 4 kilonewton per meter. So taking moment about A, moment about A equal to 0, VB dash into 200 meters the span minus 4 into the loading span is 100, 4 into 100 into 100 by 2 equal to 0. So what is the answer for VB dash? It is 100 kilonewton. It is 100 kilonewton. And to find VA dash, which is equal to total load minus VB dash, the total load is 4 into 100 minus VB dash is 100. So it is 300 kilonewton. So 300 kilonewton. So we got VA dash and VB dash. So in our cable with the stiffened girder, we obtained VA dash and VB dash, and we need the H1, the reaction H1 at the girder level due to the live load only. You have to remember the point that the girder is analyzed only with the live load because the dead load represented the cable's self weight. So it is accounted for the cable analysis only. So we have to calculate the horizontal thrust. The direction of H1 and H2 at the cable level will be little bit confusing. It is only action and the reaction component. The action is due to the live load and the tip of the cable, there will be a horizontal reaction at the girder level, which in turn converting into a reaction at the cable level. So the inward force at the girder level will be turned out in the direction of outward at the cable level. Okay, if there is a difference of live load occurs in the girder, then the reactions at the girder level and at the cable level in the horizontal direction will be different. So our idea is to, I'm listing the calculation of VA dash and the VB dash and the H1. This all due to live load. H1, how we can calculate H1 means then we have to take the moment about at the center. We have to take moment about at the center because in the girder we will have the moment value. In the girder, we should not take the moment at any point equal to 0. We will have some value. If you consider the central span, VA dash into 100 minus H1 dash into 25 will give some, and also we have to account the live load. It will give some moment value. From this moment value only, we can calculate H1. So the basic H1 equation is, if you take moment about any point or any distance, you consider at the center. The moment is at the center, which is equal to H1 into the dip. Moment at this point equal to H1 into Y. H1 into Y is the moment at this point. So H1 is M by D, where M is equal to the moment due to the live load, VA into X, and any particular loading should be added in this equation. So the H1 is calculated from the equation moment divided by dip will give the horizontal reaction here. So with this horizontal reaction H1, we are going to cable level. In cable level, here we only consider live load. So in cable level, we are going to consider dead load. The total load is the load due to live load as well as dead load, and the load can be converted into equivalent UDL, or it can be calculated with the actual live load. Here there are two situations. If you convert the dead load into, actually the load is as a area load, that is if you have some in kilonewton per meter, the live load is also in kilonewton per meter, means it is converted as a equivalent UDL throughout the cable. But here the live load is only acting over a half region. We should not take into equivalent UDL throughout the span. It will be reflected in the solution answer. It will give some difference of value when calculating the live load as a equivalent UDL, or when the live load is considering actual load. So if you consider as a equivalent UDL, you will get some approximate value. If you consider the actual live load for your calculation, that is half of the Spanish loading, you will get exact solution. So in this case, we are going to consider the actual live load location instead of converting into equivalent UDL. How we can convert into equivalent UDL means, you will have the H relation, H is equal to WL square by HD. Here if you find W means it is equivalent UDL. From the value of H, you can convert into equivalent UDL. If for this live load, from this H1 value, you can convert into equivalent UDL, which is acting in the KB section. How it is acting means, originally the live dead load is acting in the cable. Dead load is acting in the cable. In our problem, the dead load is given as zero point 0.5 kilonewton per meter square. This value is given for both the two stiffening girders on both sides. So I am going to divide by 2, half into zero point 0.5 into, and I am going to multiply with the width of the rod. Okay, then it is coming as 2 kilonewton per meter. So this is actually the dead load along the cable line throughout this span. But here, due to this live load, because the live load is acting only half of the span, we can't take it as a UDL throughout the span. So there are two chances. One, we can make it as equivalent UDL, which is acting in this like this, or we can take as actual loading. If you calculate from this H1 value, you get W in kilonewton per meter, that is called the equivalent UDL. If your problem is mentioned with the different live loads at different positions, you should not convert the H1 into equivalent UDL. You should go with the direct method of taking the live loads. Okay, next we pass on to the horizontal thrust calculation, because we found VA dash equal to 300 kilonewton and VB dash equal to 100 kilonewton. To find horizontal thrust. H1 due to live load. Due to live. So first of all, the basic formula is moment, that is girder, cable level. If you take moment about this point, here is your horizontal reaction, y is your depth. You can make a relation moment equal to h1 into y. Moment equal to h1 into y. So h1 equal to moment by y. If it is a central point means moment divided by dip d. Okay, in our problem, we are going to calculate the bending moment at the center point. What is the bending moment at this center point? Here, moment at center, VA dash at the girder level. We have to mention wherever it is needed. At the girder level. We are only dealing with this girder level. VA dash into the central distance 100. It is rotating in this direction. Load is rotating in this opposite direction. Minus 4 into 100 into 100 by 2, which is equal to, we have VA dash as 300. If you substitute this value, you will get the bending moment as 10,000 kilonewton meter. So you got m value at the center point and you have the d value which is equal to 25 meter at the center. Then h1 is equal to 10,000 by 25, which is 400 kilonewton. So this is due to live load. H1, which is the horizontal thrust due to live load. Okay, we have finished the calculation at the girder level. Next one, cable analysis. First, we understand for what we are doing this calculation at the cable level. We need the vertical reactions VB and VA and H total horizontal thrust due to live load and dead load, so that we can calculate maximum tension at this point. For this calculation, we can convert the dead load into an equivalent UDL, or we can make another calculation, that is, um, okay, we first convert into equivalent UDL. So because the dead load is given as 0.5 kilonewton per meter square for two numbers of two hinged stiffening girder. So half is considered for one side and 0.5 is the loading, 8 is the width. So you will have 2 kilonewton per meter as the UDL format. For the cable analysis, to find the horizontal thrust, we have direct formula. Horizontal thrust due to dead load, because we are dealing only with the dead load. Due to dead load equal to, we will have HD WDL square by 8D. WD is 2, L is 200 squared by 8 into 25, which is 400 kilonewton. 400 kilonewton. Okay. In previous page, we got horizontal thrust due to live load is 400 kilonewton. Here, the horizontal thrust due to dead load is 400 kilonewton. So total horizontal thrust due to dead load plus live load equal to 400 plus 400 kilonewton at the cable level. So which is 800 kilonewton. So we got H is equal to 800 kilonewton. Now it is the time to calculate VA. I already told that at the girder level, the load is acting partially. So we should not make it is an equivalent UDL and apply here with the dead load and calculate the H. It is a wrong methodology because it will give some approximate value of H. So we as it is consider the actual loading. Then here the girder position is here. The actual support reaction at the girder position is VA dash and VB dash. Here the support reaction at the cable level is VA. So the VA dash is considering the live load and VA can be calculated with the dead load. How the VA can be calculated? The dead load is uniformly distributed throughout the cable, which is 2 kilonewton per meter. Actually, it is the dead load. So the support reaction VA VB can be calculated as VA equal to total load by 2. So 2 into 200 by 2 equal to 200 kilonewton. So VA equal to 200 kilonewton. From our previous calculation, VA dash equal to 300 kilonewton. So the net total vertical reaction equal to VA plus VA dash, which is 500 kilonewton. That's all. Here we consider only the equivalent load of dead load. It is correct as per the concept, and we are not converting this half of the live load into equivalent UDL. That is also correct. And we consider the vertical reaction, which is calculated from the actual loading at the girder level and the vertical reaction at the cable level, and summing up to get the total vertical reaction. Now you got VA plus VA dash at this level, which is equal to 500 kilonewton. So now maximum tension in the cable equal to, here VA which is 200, VA dash is 300. In other side VB equal to 200, but VB dash is only 100. So this support will give the maximum tension because of the 500 kilonewton of vertical reaction. Maximum tension is equal to VA square plus H square, which is 800 square plus 500 square, which is equal to 943.4 kilonewton. So this is one of our solution. The total questions asked for to find out bending moment and shear force at 60 meter and 150 meter from left, and the maximum tension. We have calculated the maximum tension value. Now it is time to calculate the bending moment and shear force. The bending moment and shear force only calculated at the girder level. Again and again I am clearing. It is only can be calculated at the girder level. So our position, center position is 100 meter. It is asked at the level of 60 meter. So we need this y, the section vertical distance y at 60 and also y at 150 meter. Another section is 150 meter. We can consider 50 meter from the right side to use parabolic equation to find the vertical ordinate y at 150, which is equal to y at 50. So y at 60 meter, use the parabolic equation 4yc by L square x into L minus x. Here yc is the maximum dip of cable, 4 into 25 by 200 square into x is 60, L is 200 minus 60. You will get one answer, and y at 50 meter from the right side, which is equal to y at 150 meter from the left side. So 4 into 25 by 200 square into 50 into 200 minus 50. So you will get two answers, which is at 60 meter I got 21 meter and 50 is 18.75 meter. You please check the answers, and it is very simple to form a bending moment equation at this section with the available reactions VA dash and H1, VA dash and H1. So the bending moment equation is VA dash into 60 minus H1 into Y at 60. VA dash into 60 minus H1 into Y60, and the loading which is 4 kilonewton per meter, acting in the direction of acting in the load which is acting in the upward direction, which is acting in the upward direction. That is a bit confusing, right? In the downward direction. Okay. So we are taking moment at this point. So it is also rotating in the same direction of H. So minus 4 into 60 square by 2. This is the bending moment. VA dash is the 300 into 60 minus 400. H1 is 400. We have to total H1, which is 400 plus 400. 400 into y at 60 is 21 minus 4 into 60 square by 2. I got 2400 kilonewton meter. Next one, this is bending moment at 60 meter. Next one, bending moment at 150 meter from left or 50 meter from right. So I am going to consider from this right side. So the right side, we don't have any live load. We have only VB dash and the Y distance at 50 meter and H1. So minus VB dash into 50. I am considering VA dash. This direction is positive, then automatically the VB dash is in the negative direction. So I am considering VB dash is in the negative direction. Minus VB dash into 50 plus H1 into Y at 50 equal to the bending moment at 50 mm from right side. So VB dash is equal to minus 100 into 50 plus 400 into 18.73. So just calculate the value, which is 2500 kilonewton meter. So we have completed the bending moment. Next one, shear force at 60 meter. So you can copy the same equation, or we can write the bending moment equation at 60 meter This is center point. Here you assume the section at 60 meter with the VA dash and UDL and H1 into Y. So the bending moment, I'm writing bending moment equation at 60 meter. Previously we have written this equation VA dash into X. I am writing for some X distance means VA dash into X minus H1 into Y minus 4 into X square by 2. So this is the bending moment equation. If we differentiate the bending moment equation with respect to x, it will give the shear force equation. So VA dash minus H1 into dy by dx minus 4 into 2x by 2, so which is minus 4x. So VA dash minus H1 into dy by dx minus 4x. So the y equation 4yc by L square x into L minus x. So 4yc by L square. If you differentiate with respect to x is one time, so L. If you multiply it inside, it is x square. If you differentiate, it is 2 times of x. So you calculate 4 YC is the tip of cable 25 by L is 200 square. L is 200 minus 2 into 60. Our first distance, section distance is 60. The same can be calculated for 50 meter from the right side. 4 into 25 by 200 square. 200 minus 2 into 50. We need this value for the shear force calculation. So please calculate this value, which is zero point 0.2 and 0.25. I got zero point 0.2 and 0.25. Please verify. So the bending moment to VA dash value is 300 minus H1 is 400. Dy by dx is zero point 0.2 minus 4 into 60. 4 into 60. You will get the shear force value, which is minus 20 kilonewton. Now the shear force at 150 meter from left or 50 meter from right side. The bending moment equation here 50 meter from right minus VB into for some distance x minus VB into x plus H1 into 1. If you differentiate the bending moment equation with respect to x minus dB plus h1 into dy by dx, otherwise you can replace this term as tan theta. Okay, minus VB is 100 plus H1 is 400 and the dy by dx is 0.25. So calculate the shear force value. The shear force here is 0. So we finished calculating the shear force values and bending moment values at 60 meter and 150 meter and reactions, maximum tension in the cable and the reactions at the girder level. So practice this problem and you understand the difference between the live load which is acting on the girder, it is not, and dead load is not acting on the girder. Dead load is the weight of the cables. The suspender cable is the dead load. Hence it is acting as in a UDL profile along the cable line. At the girder level, you deal only with the live load. At the cable level, you sum up the dead load and live load for the overall reactions. Thank you.